Good morning, everyone. Welcome back to a little bit more COMP1511. I'm your host, and with me is the lecturer in charge. She's just here, chilling out on my lap at the moment. Trying to get her to look at the camera, but not sure if she cares right now. She's just like, wants somewhere warm to sit. Now that I've just fiddled around with my camera, I'll fix it back up. How's everyone doing? I hope people are starting to grasp the new stuff that I've been throwing at you. Structs and pointers. I mean, pointers are something that when did I introduce them? It's like week 4 or 5 or something like that. Just to start the idea going into your head, and then I've kind of brought it back again and again and again. Trying to, every time I bring it back, talk about it in a slightly different way and how they can be used and things like that. And I think the way it works will hopefully be sort of settling in now. We're obviously going to be continuing using them, so everything has been building up with what I've been teaching you to the subject that I'm going to teach you today. So one thing I'm teaching you is about how we can use more than one file in a project. I should actually go to the slides. I've got intro slides for this stuff, but let me just finish what I was saying and I'll go there in a second. But the other thing that we're going to talk about is linked lists. Linked lists are going to combine everything that we've learned so far. Well, not exactly everything, but a lot of the complex topics that we've learned so far. We're going to put them all together into this data structure which opens up basically a new world of looking at how we store and manage information on a computer. And it has all these ramifications that continue onwards for the way that computers are used. For example, the sort of big famous form of AI at the moment, which is I was about to say taking the world by storm, but I didn't want to use that phrase, and then I said it anyway. Neural networks use this kind of data setup in a sense for their main structure. A lot of fundamental theoretical programming uses this idea as well. So I'm going to teach you the most basic form, which is a linked list, and then if you decide to go further into computing, you'll see how we can turn linked lists into much more complicated structures that give us the power to kind of track connectivity between data, which is a very powerful thing to be able to do. It's so powerful that it's kind of the way that the human brain is designed. Like every time we have a thought, a neuron fires off in our head, and what it does is it sends signal across these things called synapses that connect to other neurons. So whichever neurons fire trigger other neurons to fire in certain sequences, and these patterns of growth of thought move through our brain. And that's happening right now when you're listening to my voice. The things that listen are firing neurons, and those things are triggering the other neurons that process what you're hearing, and then the others are hopefully, I can't say this for certain, but hopefully triggering other neurons that are saying, okay, store this information, I'm going to need this later. You will find out during the exam that somewhere along the way the neurons that were supposed to store the information may not have done their job, but we'll see how we go with that. Okay, let's get into it. So, what did we learn last lecture, which was Tuesday? We started thinking about memory and structs. So we were looking at our ability to allocate memory. So one thing that we'd been seeing when we were working with scope, which is curly brackets. Anytime there's curly brackets, anything that's created inside the curly brackets is going to disappear when the curly brackets finish. But sometimes when we create things inside the curly brackets, we want them to last longer. And sometimes we create something in a function that we want to last longer, and that's the kind of thing that we will do by allocating memory. The other thing that we were doing was creating our own... Ooh, hang on a second. How's my stream? That just spiked downwards really quickly. I wonder, I'm wondering what's happening on my computer. let me just make sure there's nothing running in the background. Oh, wait, you might be talking to stuff in the background. I don't know. Hopefully, people are saying there was lag. Definitely there was, because I just saw my my upstream just spike downwards really, really quickly. Trent saying it's a good time to buy a new PC. It is a good time to buy a new PC. It's nearly getting to the end of the year, and the end of the year is a little bit of time off and some gaming time, so I have been thinking about that actually. I did have that thought. Okay, my output stream is back up, so I think that's okay. David, did I forget to turn off the malloc loop? No, the malloc loop is off, and that was running on VLab anyway. I was risking someone else's computer instead of my own. Wasn't programming locally with that. Okay. So we're talking about allocating memory, which was the ability for us to have something to exist outside of just the scope of the function that it's in. And we saw the usefulness of this, where I could set up a group of items and have a function to create each one of those items, which is really going to make my code a lot easier to read and a lot easier to write, without necessarily having to say every time I create this thing has to be within this scope. I can say, no, I'm just going to have a function to create these things, and the function's going to make sure that they exist longer than they would have otherwise. The only caveat with that is we have to remember that anything that we create in that fashion, anything we use memory allocation for, we have to make sure we give back to the system when we're done with it. Otherwise, as David was saying there, if you forget to turn off the malloc loop, you use up, as we saw, I could use up 8 gigabytes of memory with this thing in about, I don't know how long that took. It was only like 10-15 seconds, and it used all the memory that VLab had available for me. And I was lucky enough that the version of Linux running on VLab just said, I'm not going to let you affect other people or other processes that you're trying to run here. This one that took too much memory, I'm going to kill it off. And then everything else will still preserve its function. So when you hit a certain point, hopefully your operating system is going to be safe enough to be able to say, no more, you've tried to allocate memory and there really is none left. So we have to stop. The other thing that we were looking at earlier on this week was making our own custom variables. So structs, which is our ability to make a new variable that is actually made up of other variables. So making a variable that has other variables inside it, but they're contained within that variable, which means that, for example, we did the Avatar, the Last Airbender characters, a few of them, and it was the idea that they had a name, so that we had a string that we could print out for their name. They also had an element that they used and a certain power level. I could get very, very Dragon Ball with power level, and I think previously I have used Dragon Ball for some of my examples, but I don't think I've got any in there this term. I swapped a few things around, so not necessarily. But we're getting to this idea that these custom variables can be very useful to us, because if I have a variable that I want to represent a complex structure, I can put all of its variables together, which is a really nice way of doing things. I mean, you could even think that in the first assignment, CS Paint, we could have thought of something like the canvas as a struct. So instead of it just being a 2D array, there could have been other information about it. So you could have a canvas, you could have some integers storing in it about its size, you could have some other information about its color range and things like that. And so you could put all this information but bundle it all into one variable, so you know you're not going to lose the information in other parts of your program. You always know you're going to access that information in the canvas itself. So we're going to have a bit more of that kind of thing happening, and I'm going to show you today how we can use the idea of structs to piece together a very interesting data structure called a linked list. So today we're going to start off with how we can work with a project that has more than one file in it. This one's an interesting one because we will actually be releasing the second assignment to you. The plan is Sunday. Furiously working in the background. One of our senior tutors is working on it at the moment. So that's happening in the background, and we're expecting that to come out on Sunday. that is actually going to be a project that has multiple files in it. So we will have a quick look today about what it's like to have multiple files and what it means. I'll introduce a couple of new concepts that we're going to use with that, and we'll look at that again next week. I think the week after. Next week we're going to continue with linked lists. And then linked lists are very interesting because similarly to an array, they will have multiple variables that they're carrying around. And they'll be the same type of variable in the same way, except they're very much more interesting because they're more openly flexible. So you don't set the size of a linked list when you create it. It doesn't even have a maximum size either. You can actually add or remove things in the middle of the list. So with an array, if I try to remove an element from the middle, it doesn't just sort of squish everything back up like that. We could erase it, but the space where it was is still there, and you have to put another number in. With a linked list, we can literally sort of remove something from the middle and have the rest of the list just kind of balance itself out like that. And linked lists come at a good point because they're going to tie together memory allocation, structs, and pointers. So a lot of the stuff that we've done in the second half of the course all comes together for this single data structure. And so it's actually so big that we're going to be covering it in 3 lectures. So it's this lecture and both of the lectures next week are entirely about linked lists. So we're going to go through all these different ways that we can work with them. So it's pretty cool. This is like the, I don't know, we could call this like the capstone topic for 1511, where we piece together all the programming knowledge we've got so far and put it all into one kind of thing. What do we got in chat? Oh no, people are just talking about 3070s and PS5s and stuff like that. We'll get there eventually. If people could please stop mining bitcoins on our graphics cards so that the graphics cards are cheaper for gamers, that would be great. There's a lot of supply and demand issues because of that stuff nowadays. Okay, so let's talk about C projects with multiple files. We've been sneaking this in. Like, this is like, I think every second topic I'll say something like this along the lines of, you've already been doing this. We just haven't told you exactly how you've already been doing this, but you've actually been doing this right from the very beginning, using hash include. Hash include is a way for us to grab another file, and up until now they've always been files that someone else has written. So they've always been C standard library files, or actually that's all we've been using, C standard library files. And what they've actually been is another code file that we bring into our project, and our compiler will look at that code file and read everything in it, and then it will read our code file and say, oh, you're referencing this thing called printf. I've seen this thing before because it was in that hash include file. So it's like we read this other code file entirely, and then we read yours when we're doing our compilation. So what we're adding to that now is the capability not only to do a hash include on the things that are written by those people who made C, but the things we've written ourselves, which we can already see is infinitely more dangerous because the people who wrote the C language, I was going to say knew what they were doing, but they didn't necessarily know what they were doing. But what they do have on us is years and years of refining it and modifying it and fixing any mistakes that might be in it. We could potentially, in the future, write code that is the same quality level as the C standard library. It would just take us a long time of getting lots of people to use it, telling us what's right and wrong about it, and us modifying things until they reach that point. But what we're going to do is learn about how we can put other files in with our code. And there's a lot of value in doing this, because sometimes it's really nice to separate our code by what it does. So, for example, when I was talking about structs and I was talking about building a team of characters, I could have the characters in their own file. So I could have a file that says, this file manages characters and the statistics of characters in say, a computer game. So I was making a computer game of Avatar or something like that. So I could do that kind of thing. And the nice thing about that is I could plug that character file into multiple different projects. And it's just the same as us saying, oh, let's write a library which is a file or set of files that is capable of doing input and output to the terminal, for example. And if we can do input and output to the terminal, we're going to use that in multiple different programs. So we'll call that one the standard input-output library, stdio.h. And then people can include that in multiple different projects without having to rewrite it. And that's like one of the things that's really nice about libraries, and we can actually do that ourselves, where if we want to, we can make our own reusable library. And it becomes just another thing that's in our toolbox, and we can say, all right, every time we need this kind of thing, we can just include this library that we created earlier. We don't have to rewrite it, you know? So there's a lot of value in being able to split things into multiple files. Because I could say, oh, I've written these files, and someone else who I'm working with says, do you have anything that can do, I don't know, advanced priority-based queuing of data that comes in? So when I receive data, I say, you're important, you go to the front of the queue, or you're not so important, you go to the back of the queue. And I say, oh, actually, I've got a library I wrote for that previously. Here, why don't you have these files? And they go, oh, great. I don't really need to work that much with these files. I can just include them in my project. And the same way as like printf and scanf and stuff, I don't actually need to know how these how these functions were written. I just need to know that they work in a certain way, I trust them, and I use them. You know, so there's a lot of value in being able to split our stuff into multiple files. But what we do need to know is how to work with multiple files if we actually have the files ourselves, or if we're writing in multiple files at once for a project. Sarvesh is saying, I'm teaching you code bending. See, that's the fifth element was abstract mathematics. It's the one that's not quite as good in combat, but has very significant ramifications for the world in general, because it's not just a physical element. It's an element of the mind. Actually, that's pretty cool. Okay. I'm thinking Avatar in a sci-fi futuristic setting where there's a whole form of bending which is about creating and manipulating artificial intelligence. And there's all these robots and stuff like that that are made by code benders. That's super cool. Anyway, let's move on. Okay, so when we're blocking the headings with our face, I'll just move myself over a little bit. We'll have pairs of files that go together. So this is a new file that you have kind of seen, but you haven't necessarily called a header file. And it'll be a .h file. So I probably had this conversation. I think I vaguely remember having this conversation with someone in a lecture where they said, why is standard input output .h and not .c? Everything we're doing in C is .c. Why is this thing a .h? And now I'm going to tell you about the .h, because the .h is a really, really specific file. And I'll show you. I've got an example for this. So we're gonna work through an example. Well, at least I'll show you an example to show you how this kind of thing works. The .h is an interesting file because it has very little code in it. But what it does is it shows what capabilities the code has, so that you know what functions are available in the code and have a decent idea about what they're going to do. You know some of the data structures that are in the code and some of the functions and things. So some of the structs will be set up in the H file. Not all of them. A lot of the structs will actually be hidden in the C file. So the C file and the H file will be linked together by the C file including the H file, so it knows everything that's in the H file. And then the C file will actually do the running code. So it'll have the actual line-by-line working of the code. I'll show you in a second. I just want to introduce what these things are and then show you what they are. I don't know if you're talking about... Oh, William saying data structures and algorithms with Andrew Taylor. So yes, wait, which one is that? Is that 2511 or 1521? Might be 15. Wait, it's one of the 25 subjects. Yeah. Yeah, I think a lot of the subjects, if anyone's continuing with computing, a lot of the subjects that continue on from this are going to use this kind of structure. We're going to use it in the second assignment as well, so that you get a bit of familiarity with it. So, the header file, I'm wondering if... Actually, I'm going to talk about it a bit and then I'll show you, but let me just establish a little bit of context by by showing you an example. This example is in WebCMS as well, in the lecture section. Lecture 12? I think it's lecture 12. Yes. Okay, so I've got this, and I'm just going to open all of these. So I've got these 3 files here. The main.c is something that you may have seen before. Oh, this is my Batman demo, by the way. This was actually from... I was doing something similar to the Avatar The Last Airbender thing with Ninja Turtles, and then someone asked me to do Batman, so I did a Batman demo, and that one stayed in the course for a year and a half, I think, since they asked me about it. Okay, so the H file looks a little bit like this. Very, very interesting. We're going to talk about this in a second. Typedef is a particular thing. I've got slides, I'll talk about that in a sec, but looking at these things, they're function declarations. So note that these are the kinds of things that we would usually put at the top of our program. So I don't think my main.c's even got any. No, it doesn't have any. But what it will do was it will include person.h, which is basically going to copy and paste. It's not exactly the same, but it's basically going to copy and paste all of this here. So if we were only ever going to use this thing once, we could technically achieve the same thing by taking all of this and copy pasting it in here, so that our main.c would know that all of these functions existed. So this is like a version of the thing that I was doing with the benders on Tuesday, where you have a character. You have the ability to give the memory back to the character, and in this case you're able to give them superpowers. So when I use those functions in here, so I create the person and then I give them these powers. So obviously these 2 are the most important ones for Batman. That's like a little bit of a joke there. These functions can work on this variable here, because we know that these functions exist and we have inputs and outputs for them. But let me go back to my slides and I'll explain the theory behind this thing, and then we'll come back to the code afterwards. But I thought I wanted to at least show the code files first, give you a bit of context for what's going on. Sarvesh is asking about, is this the same kind of thing as object-oriented programming? It's a little bit similar in theory to object-oriented programming. It's like one of the parts of object-oriented programming is this kind of thing where we separate things. And we separate things and say, you can't access this code directly, you access this through an interface, in a sense. I think that's the abstraction part of object-oriented programming. We're going to actually talk about this later in week 9, where I teach you some bonus content, which is a little bit stretch goaly for COMP1511. We're going to look at these things called abstract data types, which is actually what this is, but we're going to look at the theory of it a little bit later. Oh, and Raymond's asking, how come there's no code in the H file? And we'll look at that in a moment. So there's a difference between the H file and the C file. In the C files, and just code that works. So actually, let's look at the C file. So the C file includes person.h, and this is actually where all these includes happen so that we can use libraries and stuff. This is where the struct appears, and this is where the function code happens. So when we think about this, when we've been working with single file projects before, we have had above the int main, we've had what's in the H file, the declarations of functions. And then below the main, so this only has a main, has nothing else in it, but below the main is where we would have all of this stuff, the implementations of all the different functions that we've created. So what this multiple file project system is doing is it's splitting these things out. So this is extra functionality that's outside of our main is actually pushed into other files. And the beauty of that is that these other files can then be used in other projects. That's one nice thing about it. And the other thing about it is now, whatever we write in the main file, doesn't actually have access to everything that's in this file, in this C file, because it doesn't ever see what's in the C file. What it does is it includes the H file, and it can only use the things in the H file. So there's a really, really nice thing that we can do here, where this main file will never see this struct. I'm jumping around a bit. I actually have slides that are going to go into this, but like I thought it was good to talk about this because we started on this tangent. It's not really a tangent, it's actually one of the core elements of this thing. Because I can never see this struct, it means I can never affect it. So if I come in here and I say, there's this thing for give power, and I'm just like, no, I just want to change that. So I go Batman powers 0. It's a string, so I would have to string copy this. None. So I come in and I try to remove Batman's ninjutsu power by saying replace what's in that string with none. And so I do this string copy where I'm thinking, I know that there's a struct there, so I want to be able to access it. But the beauty of this system is in person.h, I get this thing called a type definition. I'm going to go back to my slides so I can at least tell you about the type definition. Where is it? Maybe it was this slide that I was going to talk. I actually was on the right slide. Oh yeah. No, that was the type def, yeah. Okay. So type def is really interesting. It's our way of nearly being able to create a variable type out of another variable type. So what we get here is struct person pointer is a variable type. So the struct person pointer says, I am a pointer to a struct, and the struct is actually defined in here. The H file itself doesn't even know what a struct person is, because it doesn't see the C file either. It's just saying that if sometime in the future we see something called a struct person, and if we have a pointer to that, we can replace that with capital P person instead. So here, if we see the H file, we see that capital P person is something that exists because it's been defined as a type. That's what type def is short for. Which means I can say person Batman. And then underneath this, when I'm using things, I can put that capital P person in and out of functions without actually knowing what's underneath. So this is why it's sort of like a variable that nearly doesn't exist. It only exists from the viewpoint of our main file to say, okay, there's a person called Batman, but I have no access to things inside, so this won't work. And the good thing about that is the only way that I can do things with that array of strings that's inside Batman. Let me just see if it is an array of strings. Yeah, so it's a two-dimensional array of characters, which we can consider an array of strings. The only way I can access that is by giving them a power. And so the beauty of this is I can't access the data directly, but I can access it through a function. And if I access it through a function, the implementation here can actually say, if you want to give someone a power, but there's a maximum number of powers that they can have, if we go over that maximum, we can't do anything to that data. The other thing is we can't change the data, we can only give someone powers. So at this point, we can't take any powers away. So what this does is says, you don't have unlimited control over the array of strings here. You can only do the things that we said you can do with this. So that way what we do is we can take a data structure like an array of strings like that, but say this is not just an array of strings. This is limited in what you can do in very specific ways. And the only ways you can work with this is by using the functions that you can see in the person.h. So when we're writing code in our main.c here, what we'll be doing is we'll be looking pretty much only at the person.h, and we'll say, okay, what does this thing do? creates a person and returns a pointer to them. So it's going to return the person after it creates it. We're going to assume that that's going to do some memory allocation and stuff underneath, but we don't know for sure, and we trust that it's going to happen. This is actually one of the ways that we do a lot of things when we're working in groups, where we will write an H file together. So if I'm working with one other person, we'll write an H file together, and we'll say, okay, so these are the functions that we need the person to be able to do, and one of us will go and write the person.c. So one of us will say, all right, I'll make sure that when I'm asked to create a person, that all the memory gets set up properly, and then I give back a pointer to the person. The other person will be working in the main, and they'll say, okay, I'm going to assume that that works. I'm going to assume that the other person gets that thing working, and then I'm going to do things with the person that's created. So it's this really nice way the H file can actually be this line between two programmers, and we say crossing over that line is where we actually we'll never actually cross over that line, but we'll do that only through these specific functions that we've decided on in advance. So there's a lot of really cool subtlety in what you can do with the multi-file projects. But I should actually talk more about the specific basics of how this works. Let me just see what chat is saying. Stefan was asking about when do we use the arrow again, only for pointers. Yeah, so I mean the arrow there that I used, actually it probably would have been, I could have tried this, something, but either way, neither of these things would work, because from my main here and my H file, there's no real acknowledgement that capital P person is actually a struct that I can access things inside. So there's only the idea that anywhere we would have had a struct person pointer, we can use capital P person. What this actually does is it allows us to swap back and forth if we want to. And so here in the C file, sometimes we'll see pointers and sometimes we'll see capital P person, depending on how we're using it. I wonder if we've got one there. So we've got a struct person pointer hero here, where we're working on it. But sometimes we will say, for example, give back a capital P person, and we can call it a capital P person, but because we know from the H file and we know the struct here in the C file, we can actually use it either way. Sorry, I'm going into too much detail here, so I'm going to go back to my slides and look at the overview of how this thing works. Gautam saying there was some lag. There might have been. Sorry, I was looking at the other screen, so I wasn't checking what my upstream was looking like. Okay, so the H file contains a bit of information so that a programmer can look at the H file and they can use all of the functionality that's in our H and C combo, so our person H, person C combo that we have there. We can use all of that stuff without ever looking at the C file, as long as the H file's got comments in it that tell us what the functions do. The type def, as I said before, is a way of saying that one word means another, and you can swap them back and forth. Usually what we're going to do with the type def is say that, yes, there is a struct somewhere, but no, you can't see it. And since you can't see it, you shouldn't think of it as a struct, so we're going to give it a different name, a more intuitive name that you're going to use. So as I was saying before, this means that the data inside the struct is not accessible inside the main. So it being non-accessible like that means we have to go through functions to get to it. If we have to go through the functions can guarantee that anything we're trying to do to it is safe. Also, the H file generally has no running code in it. Rare occasions we may implement something in the H file, but I would nearly take it as a rule that there's no running code in the H file. It's only declarations of functions and a type def. So in the C file, we get the link between the C file and the H file. So in order for the C file, so the C file is going to have the running code for every function that's in the H file. So we can consider the H file nearly to be a table of contents and the C file to be all the chapters actually written. The interesting thing about it is the computer is not fussy about a table of contents being ordered the same way. So you can order the functions in a certain way in the H file, and you could write them in a different order in the C file. I mean, I wouldn't, because as a human who needs to read the code, I would still want to be able to go through and read it. But you can do that. In order to know what it is implementing, it includes the H file. This is the thing that joins the two of them together. So the C files tend to include H files. That's the way that it usually works. You will basically never include a C file. If you think you need to include a C file, it's usually there's a confusion that's happened there, and potentially it means that something that should be in the H file got moved to the C file by mistake. So the structure is nearly always going to be C files include H files. When they include H files, so when the main includes the H file, it is seeing what someone else has built for us so that we can use its capability. When the C file that matches the H file is including the H file, it's saying, these are the things that I need to make sure I make the running code for. So when there's a type def in the H file, the C file will have the actual struct that the type def is linking to. So that's the kind of hidden data structure that the main won't know about. And the main will only be able to see that it is an idea, not the details of how it's implemented. And the C file will obviously also have all the code in it that implements what's in the H file. When we have our main file, and this also can get more complex because it's not just a main file and one set of other files. As we've seen previously, I mean, I could just look at this here. This idea of a multi-file project here, we've got 3 of our own files, and we've also got 3 files, 3 other complete setups that are in the C library that we can include as well. So each one of these things has its own things, and it may include other things as well. So there's this chain of stuff including each other that that can be really useful, you know, because it means that when we say I want standard input output, we actually get all these other things as well that we can use stuff from. Either way, what happens is the C file is going to include an H file, and when it includes the H file, it gets to see what functions it can call. So it can say, I can use these functions that may exist somewhere, and they're going to help me do what I'm doing. So when we're... oh wait, I jumped ahead a bit there. Yeah, so when we're including these things, we get access to them in a certain way. When we're compiling, everything just goes into a pile of code that has capabilities. But when we include the H file, it means we know the names of things. If we know the names of things, we can access them. Okay. The one thing that we need to remember, though... Ooh, Raymond, good question there. Actually, let me just see what other questions we've got. Izzy's saying, what would be the point of having an H file where you can't see the code? Couldn't you just have a C file with the function prototypes and look at those? Yeah, so there is a way we could think of to say that, why don't we just include the C file and have the C and H file combined into one piece? So it's just like, I want to include this entire module and all its capabilities. The reason we don't do that is because if we included everything from both the C and the H file, then my main would be able to see this. If my main can see this, it means that it opens up this person. So the person who's working on the main, it opens them up to being able to access these bits of data. And if they can access these directly, then it's unsafe. So it's unsafe if they can change stuff in the data structure that's not using these functions that are careful to only make changes that are safe. So we can consider the C file to be written by someone who's managing and protecting this data structure from any kind of mistakes. And this to be the person that says, I want to be able to use this thing safely, so I will only use the functions given to me. So one example, this is actually going into the lecture that I'm going to talk about abstract data types later when I'm talking about this, but I'll bring that up again later when we get to it. It's in a couple of weeks. This person is driving the car, and this person is building the engine of the car. So you get this different kind of viewpoint on things where this person can see the engine, can see what its capabilities are, make sure that it only gets used for its proper capabilities. This person's just hitting the accelerator. So if I call this function, I don't know what it is, that's like me pressing the accelerator in the car. So when I'm driving the car, I'm assuming for the moment that we don't have mechanical engineers here who do know how this works, but a lot of us who don't know how this works. When I press the pedal on the car goes forward. What I'm not knowing precisely about what's happening there is that when I press the accelerator on a car, that changes the amount of fuel that goes into the engine. That changes how fast the engine is spinning. What that then does is it drives the drive shaft of the car, which is the thing that sends power eventually to the wheels. There's much more detail in this, right? But I don't know it. I just assume that when I press this pedal, the wheels are going to start spinning more than they were previously. So from this viewpoint, we have that. If, for example, I was sitting in a car and driving it, I had full access to the engine, so I could like poke at the engine itself and like grab the other end of the accelerator, which is like adjusting what the fuel air mixture is in the engine itself, and I started playing around with that myself, I could actually blow up the engine. So it's better that I don't have access to those things and all I have is a pedal inside the car, and that's all I can see. So this is what's happening here, is from this perspective of including person.h, I don't get to see how anything works. I just get given these specific functions that give me the capability to do things without the specifics of going in and doing things like this. So what we do is we trust that those things work because we're kind of operating them from an outside perspective, but we don't want to give that access. So for example, if we included everything, we would be able to see this and we'd be able to edit the name anytime we want without necessarily saying that the intention for this data structure was not for you to just go in and pick at it and things like that. So hopefully that explains why we're separating these things, right? Because we're actually nearly protecting ourselves from making mistakes with them. Gira-chan saying, if we only have prototypes in the H file and include them in our C file, how does the C file know what the function definitions are? So this is an interesting thing, right? So if I include person.h, all I can see is this. So when I call it, what happens? So when I call display person, I go to here and I go, yeah, display person. But how does our program even know that, that this code even exists? Because when you look at it, this can only see the H, this can only see the H, which means there's actually no connection between these. But the way that we compile our code will actually put all our code together into our library. I mean, code libraries. We've already talked about libraries, which has all of the functions in it. And if you know the name of the function, you can access it so long as it's all been compiled together. So remember that when we do our compilation, actually, I like it when people ask me about things that are in my next slide. When we do our compilation, we create a program file. And the program file has all the possible running code. When we compile a multi-file project, it actually takes multiple code files and pieces them together into a single program. So let me show you this happening. So the way that we compile when we're compiling a multi-file project is we will compile the C files, but we will not compile the H files. The reason why we don't need to compile the H files is if an H file is important, it will already be included. So this H file is important, it's already been included, so we don't need to compile it. Whereas you can see the C files are disconnected, so we need to compile all of them. So I'd compile my main.c and my person.c. So this means that both C files go into the program code. Let's call this person demo. And when I'm done with this, I have one file. So what I've done now is I've actually combined two C files and whatever header files that they were looking at. So the person.h is going to get included, but on top of that, the standard library, the string library, and the standard input-output library are going to be combined as well, which means that this program here is made up of the code that's in main.c, the code that's in person.c, whatever code we needed to access in the standard library, the string library. Wait, string library? Was the string library there? It was the standard library, yes, the string library and the standard input-output library. all of that code is combined together into one program, which means that this program can access all of the functions that are available in all of those libraries, including the person library, the person.h library. But it also means that if I look at the person.h and I say, can you run display person? It will say, do we have in this program, do we have a function that can run called display person? And so what will happen when you call that function is this program will look through all of the code that it's compiled and it'll say, oh, there is a display person function. It's part of what we compiled, and it will be able to find this and it will be able to run it. But the only way we'll be able to find that is if we know that it exists, because we know what its name is. So everything's kind of linked. Like, this is actually a technical term. There's a compiler and a linker. And the linker is the thing that says there's a name somewhere, and there's code attached to that name somewhere, which is this code here. And when we run from here, it'll say, can we find this? You know, and it'll look through the code and say, can we find this? Because we know that it was defined somewhere, so it's real, it should exist. And then we'll look through our compiled code for this. Actually, interesting things you can do if you want to play around with this project is try to compile it, run it while you've commented out one of the functions. Because I think it will still compile, depending on how good your compiler is. Very good compilers will notice that this has not been implemented, and will say that there's a problem on this line. More regular compilers will say, this links to this, there's no real problem. But then when you run it, it will say that if you've commented this out, it'll say, I couldn't find that function. So you had a function, you defined the function name, but I couldn't find an implementation for it, so the program has to stop here. So you get that kind of thing where you see when your program looks for different things. Okay, so compiling is going to work like that. We will compile only the C files that we're using, and we will use #include to include the necessary H files. Be careful that amongst all the C files, so we can't just throw in multiple programs together, because there can be only one and exactly one main function. Because if there is more than one main function, then when we run our program, so for example, /person demo, this is going to do some of that stuff. So Batman at the beginning has no powers, and then later on Batman has many powers. The power of being a ninja, having a lot of technological gadgets, brooding on gargoyles, and having a gravelly Christian Bale voice with which to intimidate people, which is obviously Batman's true power. What was I going to say there? Yes, when I called this, when I ran this program, the thing that runs first is the main. Usually we're really polite to ourselves and other humans by putting the main function in a file called main. Because when these things get complicated, and you've got like 15 files or something like that, you don't know where the main function is. It's really hard to see what the program is, or where the program starts. So what we will usually do is we have a file called main that has the main function, and it makes it easier for us to find it. There can be only one main file. There can be only one main function. If we put another main function, say in the person.c, then our program will not know which of these main functions to run at the beginning when I call this. Because when I call this, it has to be exactly one function that runs, and no confusion about that. If I was to have just all these libraries with no main, and then I run this, then nothing runs, right? Because there would be no kind of entry point into the program. And Raymond's saying, will we have to do anything with the 15 files like that? It depends how deep you want to go into computer science. We're not going to be doing that in COMP1511. That would be a bit much. Okay, so I've got slides here for looking at the Batman project, which I'm not going to need to go through because I actually kind of went through that and interspersed that into what I was talking about. So I think I've covered all of this stuff already. So, and the compiling here as well. And so this is what we're asking here. A couple of people are asking about using multi-file projects in COMP1511. So in 1511, looking at these multi-file things is going to be pretty simple. So technically, and I'm thinking about this carefully, I'm pretty sure we're going to be in a situation where you can 100% this course without actually creating a multi-file project. I have to be a bit careful with that because I haven't written the whole exam yet, so I still might want you to write a multi-file project in the exam, but even that, it'll be really simple. So your second assignment is going to have a multi-file project in it, but we will have created it for you. You don't actually have to do anything with the file structure. You don't have to create these things from scratch. I understand, and I know because I learned this myself years ago, that these are not the kinds of things that you grasp really easily and start building on your own really easily. So what we're generally going to do is show you a few different ways to use them first, and then you'll get an idea about how you want to build them, and then if you continue on to other computing subjects, then you'll eventually be asked to build these things yourself. So there was trepidation in chat there about like how much we would have to know about these things, and so what I'm saying is it's not a huge amount yet. So that's all I want to say about multi-file projects. If you want to, you can play around with the Batman project and see how that works. I am going to be creating more multi-file projects in 1511 in lectures as we go along. We're going to see some in tutorials and labs as well, and obviously in the assignment. Actually, we won't do it that much in the tutorials and labs. We'll discuss it, but because it takes longer to build these things, we probably won't build that many of them. But we will definitely be using it in the assignment. You'll get an idea of how that works, but you won't necessarily have to build any of these. Okay, next thing that I want to go on to give my voice a break for a second. This is something that is definitely going to be in the second assignment. The second assignment is based on this structure here and the ramifications of what it can do. I'm going to show you a structure that is called a node, but we will be giving this thing different names depending on what its purpose is. But the very interesting thing about this structure that I have here is it contains some information. So the node carries some information, but the very, very important thing that's going on here is I have a pointer to a node in the node. So very, very interesting, because a lot of the time we think that we can't actually access a struct until we've completely declared the struct. But what we can do is we can access a pointer without necessarily knowing exactly what the pointer is aiming at, because we know that pointers are always going to be the same size anyway. So we know that this pointer in my operating system, 64-bit operating system, is going to be a 64-bit variable. So I can actually declare this thing without actually knowing fully what a node structure is. The cool thing about having a node pointer inside the node is what I can do then is I can link this node to another node. So I can say, I have a node, has some information, and a link. And then I have another node, and that has some information. We chain these things together, and we can create a list. So if I just had a pointer somewhere that said, show me the first node, the node carries some information. And so this is this struct in my not to scale memory. And I have a pointer in here to another node. If I have a pointer to another node, this could be another node that I've memory allocated. So if I've memory allocated this other node, it has this other information in it, and it tells me who's next. And this node tells me who's next. And then this node, and this is where we're actually going to use that null keyword that we haven't used that much yet with pointers. If this node says the next pointer is null, that's it saying there's no one after me. So that way I can say, okay, that's the end of this list. And so what this will do will allow us to store data where we can have some information and we can say who's next. And then what we can do is we can follow our data through to other information like this, and we can say, going from here, go to the next step and read this information, then go to the next step and read this information. I like to think of it as like those old school pirate treasure maps, where like you go, okay, go here, and then once you're there, you have to dig up this information, and that gives you a clue of where to go next. And you go, oh, so we dig up this treasure chest, but there was no treasure in that treasure chest, but there was information on where to go next. So that's like me saying, look at this node, and then I don't know where this third node is until I've seen this second node. So the first node has no information about the rest of the list. It just goes, I only know who's next. And then here, this one says, okay, now I know who's next. And now I know who's next. And eventually this one says, I'm the last one. That's everything. So you've gotten all the data that we were all storing. Girochan's asking, is there a counter for the nodes? No, there is not. So when I am here and I've appointed to the first node, I actually have no information about how many of these things are. The only way I can figure out how many things are in this list is by looping through the whole list and finding it. However, it doesn't matter how long or how short this list is. If I'm looping through it, I will be able to see all of the things without needing to know how long it is. Because all I do is I just keep skipping through these next pointers until I get to one that says there's no more. And if there's no more, then there is no other memory here because there was no pointer aiming at some other stuff, and that's how I know I've reached the end of the list. We'll talk about looping when we'll get into that in a second. So the interesting things about this kind of structure. So you can see how what we're using here is memory allocation of a structure. So last lecture we looked at memory allocation of a structure. This is a particular structure where you can memory allocate it and then you can assign its pointer to another memory allocated structure. It doesn't even have to be memory allocated. You could just declare these in code if you want to, but we're mostly going to memory allocate these things. As I said before, when we're using structures, it's very, very common for us to memory allocate them, and so I was leading towards this idea. So let's look back at what our arrays are, because there could be a question that everyone's thinking of, which is, why are we using these things when arrays are actually pretty simple to use? So an array, remember, is a single block of memory. It's a single block of memory with multiple variables in it. A linked list is not a single block of memory. Every individual node in the linked list is its own block of memory. So that's interesting to begin with. If it's not in a single block of memory, it means it's more flexible. So we can shuffle things around just by changing pointers. So let me just... I was like, open CS Paint and then draw your diagram. I'm not going to do that. So let's say I've got this really simple linked list. I've got these things pointing at each other, and I want to reorder these things. It's actually reasonably easy for me to say, okay, let's just take this pointer and move it to here, and we'll take this pointer and get rid of it and have another pointer here, and I can reorder my list just by flicking a few pointers around, as opposed to an array where I would have to do something where I would like maybe copy all of the contents out into another array and then copy the elements of the array back in the new order that they're going to be. So linked lists have this kind of capability like this. And if I want to, let's say for example, I want to remove this item from the list, I can actually also do that with pointers, where I will no longer have that pointer aiming at that item in the list. Oops, do that in the color that the pointer was. I can instead go, okay, this pointer aims here instead. So I can just cut things out of my list, and if I want to, I can even add elements to the list by moving pointers around. So if I want to, I can say, put this new element in the list in between these two, and then what I do is just fiddle around with these pointers and say, okay, instead of that one aiming at that one, it can aim at this one, and then this one can aim at that one. So just shuffling pointers around like that allows me to do a lot more manipulation with how these collections work than I could do with arrays. So the other thing is, like we were talking a second ago about the length is not fixed either. David saying I should draw my diagram in CS Paint. All the zeros and fours. Yeah. So you can see already how there's a lot of flexibility in this. But to get that flexibility, we must understand a lot more about how these internal structures work. So how does a pointer link two things together? How does memory allocation work so that we can have separate memory, not just one big block of memory? So you get that kind of thing where if we have an array that's, say, length 10, and you go, I want to add an 11th element to this array, the array just says, I can't do that. I had one block of memory, and I can't just get bigger. Because if I try to get bigger, what if there's other stuff directly after that array? What if those are other variables? I would have to, best case, I would have to pick up everything, shift it all to somewhere else in memory that's bigger, and then get larger. And that's a really hard thing to do. Whereas the linked list is like, oh yeah, that's fine. Just allocate some memory anywhere in our program, and we'll have a pointer to it, and we can get longer. So the only limit of how long a linked list can be is how much memory you have available. So all those 8 gigs that I was using up previously. And so that's really cool, because what you do is at the beginning when you create a linked list, it takes up no memory at all. And then as you add items to the linked list, they slowly take up more memory, but they only ever use as much memory as they need. As opposed to an array, and you've seen this before, right? You've seen this in lab questions and stuff, where you say, store this stuff in an array. We think at most you will have to store 1,000 things in this array. So you say, okay, if you said I have to store a maximum of 1,000 things, I have to start off with an array that's 1,000 long, and then all of our auto tests only test you on like 10 items or something like that, and you're just like, oh, well, we used up all this memory and we never actually used it. But it was like, we didn't know how much we were going to need. So with an array, we had to allocate it all, in a sense. We had to say, we need to have all the space for this stuff just in case the input gets big enough to use it. But with a linked list, we can say, no, you just use exactly as you need, and as more stuff comes in, you allocate more memory as you go. So there's this kind of different flexibility going on there with that. Okay, so about to go on break. Ooh, hang on. I'm going to be the big brain. It's all about putting myself in the memes. So I like this meme because this is us building up our knowledge of programming so that we can reach the point of linked lists. So we can allocate memory so that things don't disappear. And initially when I said that we could do that, you'd be like, oh, I guess I can see some use for that. But now you can see if I can allocate memory, it means I can create these data structures that continues. And then we can allocate memory for structs. So it's not just a single variable, it's a multivariable variable, which is what a structure is in a sense. And then we can have structures with pointers to their own type. A structure with a pointer to its own type is really interesting because it means it can continue to kind of sort of propagate in a list, and then we get linked lists. So linked lists are combining together structs, pointers, and memory allocation. And they're also doing this kind of self-referencing structures, and they're putting together a lot of stuff we've learned recently, like structs, memory allocation, and things. So this is kind of like the big subject that we're going to be working on for a while. And so we'll take a break now, and then we will start building some. So we're going to talk a little bit more theory about linked lists. So we're going to actually start building some. We're going to have an example that lasts all the way through from this week through to next week. We're going to build up this whole thing using linked lists. Girachan's asking, where's the Spider-Man linked list meme? I already used that meme. I can't use it again because I used that meme when I was talking about pointers aiming at pointers. So when I said pointers to pointers, I had that meme and said, don't worry about it. We're not going to do them just yet. Okay, let's take a break. It is 12:04 by my clock here, so we'll come back at 12:09. We'll take exactly 5 minutes break. See you in a second. Alrighty, we're back. So, I have introduced the idea of what linked lists are, but I want to show you a bit of the implementation of this, and then some of the things that we can do with it, and then we're actually going to make these things happen. So let me just put myself back up in the corner there, and we will continue. Right. So we're going to build up from the beginning. We're going to build up the simplest possible list. We're actually going to build this whole thing from scratch, but I'll start the example later once I've shown you a little bit of what's going on here. So, simplest thing we need is a node. And really, to build a linked list, the only thing we need from the beginning is just this node structure, and then everything kind of flows on from the fact that this exists. So, we've got a node, and in order for us to know where the list starts, we need a pointer to a node. And then we're going to need a function that's going to create a node, and potentially as it creates the node, it'll potentially connect it up to other nodes as it does that. So we can already think about some of the ideas about how this stuff is going to go together. So we're going to have something like this create node function. And so we've seen this kind of function on Tuesday when I said we can have a function that what it does is it creates a struct, and what it returns is a pointer to the struct. So no different here, it returns a pointer to the struct, and then what it takes as input is potentially the stuff that's going to go into the struct. So on Tuesday it was just like a couple of strings and a number, I think it was. So we were putting in the name of the person, the element they use, and their amount of power. Now we're doing a very similar thing. So we're saying the struct is made up of a pointer and some information. By the way, that information, I have an integer here. It can be kind of anything, because this is a struct. So when we consider what information is in each node of our linked list, we can have lots and lots of different possibilities. So for example, if I wanted the linked list, if I wanted the group of benders on Tuesday to be in a linked list rather than an array, then I could have in the data here, instead of an integer, I would have a string for their name, and then I have another string for their element, and then another string for their power, and then integer for their power. So this struct could get much bigger, and that's fine. That doesn't change the fact that it's a linked list. The thing that makes it a linked list is we would say the information that goes inside we can take as input, and then we will set up our memory allocation of node amount of memory, and then we'll set up the information that's inside. So the pointer to next and the and whatever information it's carrying, we'll set that up, and then we'll return the node that we've just created. So very, very similar to what we did when we were making just a struct and memory allocating it. The only subtlety is that this pointer to another node might have some more ramifications depending on how we're linking it up to other things. So if we wanted to build a list and all we have is the ability to create a node, we could actually still do this. So we can have a pointer, and then you'll see this word coming up a lot. The head of the list is what we consider to be the first element of the list. This becomes quite important to us when we're working with linked lists because we can't see anything else in the list. So our only capability is to be able to see, are you the first node in the list? And we go, okay, if we've got the first node in the list, technically we have access to all the others, because if we just follow their next pointers, we'll end up looking at every element in the list. So we want to always maintain a pointer to the start of the list. So if I want to make this list with all of these numbers in it, the first thing I do is I say the head of the list, and we create a node for the head of the list. And then what we can do, this is a weird way of doing it, because what we have is we have the start of the list, and then we make a new node, and the new node becomes the new start of the list, and it pushes the other node along. And then we make another one, and it will push those two along, and it will become the new start of the list. So I create node number 2. Node number 2 becomes the head of the list. But node number 2's next is aimed at the old head of the list. So I've got some diagrams here to show you this. So first thing I did is create node. with a number 1 in it and null as its next. So when I know that there's only one element in the list, I know that its next will be null because there's nothing else for it to point at, right? Because I haven't got any other nodes at this point. I've only got one. Then, when I say things are getting pushed along, they're not moving. They're actually staying where they are in memory. But then I make a second node. So that first one didn't actually move. It only moves in my diagram, because my diagram's not to scale. So I make a second node here. Its next points at this node, and then the head pointer moves here. Actually, you know what? Gonna draw this for you. So, when I call my first create node, let's go back to the code. My first create node here, I have a head pointer. So let's just say my head pointer is going to aim somewhere, because I know that I've made a head pointer and I'm going to assign it to this. So create node is going to memory allocate some memory there, and my head pointer is going to be aimed at that memory. It's going to have the number 1 and a null pointer. So let's just say it's got the number 1 in it, and then it has a pointer coming out of it that points at null. Then this next line is first going to create a node with 2 in it that aims at head. So let's create another node, and we don't actually know where these things are going to be in memory, because whenever we call this function, it's going to call malloc, and malloc is going to talk to my operating system and go, you got any spare memory? And malloc says yes, because you turned off that malloc loop that you did last time. So we've got 8 gigs worth of memory for you. There's all this space, so I'll give you some space over here. It's like, okay, cool. I didn't need it to be anywhere in particular. I just needed the space to exist. And then the 2 was created with the data 2 and aiming at head. So aiming at head means it takes a copy of this pointer. So this pointer was aimed at this location. I take a copy of that. So I'm also aimed at that location. So my pointer is now aimed from my 2. My next pointer is aimed at my 1. My 1 next pointer is aimed at null. And then it says, when you're done with that, assign the output of this create node to head. So if I'm assigning the output of a function, and the function outputs a pointer to head, what I am doing is I'm changing the memory address that is stored in head. So changing the memory address that's stored in head is going to change where it is aiming. So the pointer, I nearly precisely erased that. So the pointer now from head will be pointing here at 2. So 2 becomes the new start of the list, and 1 has been moved to the second location in the list. And you can see we did that without actually changing 1 at all. So we didn't change its data, we didn't change where it was pointing, we just changed the pointers that were leading up to it. And we can continue doing that if we want to, so we can continue making new things, pointing head at the new thing and pointing the new thing at the rest of the list, and we can just keep building up a list like that. This is the simplest way to build a list. It's definitely not the only way to build a list, but if we want to do it in the very simplest way, when all we know at the beginning is how to create a node, we can still have a linked list. So this is what was happening there. So we had our 1, we put our 2 in front of our 1, and we moved our head to the 2. We could put a 3 in front of the 2, and then put the head there. So we could have that if we wanted to just continually add nodes to a list, and all we had was a create node function. So that's actually pretty simple. We can do that in a quite an easy way. The next thing that we want to do, after we have the capability to create a list, we have to think of how are we actually going to look through a list. So if we try to kind of wind back to the idea of arrays, we had a tried and true method for looping through an array. It was we know how many things there are. We know that the indexes are a sequential order of integers. So in order for us to loop through a linked list, this should be easy. For us to loop through an array, it's easy because you just go through the numbers. right? And so we've done those while loops. We have I, and I just increases. We can't do that with linked lists. We don't know how many of them there are. They're kind of scattered around in memory. Remember, the index into an array is actually a memory offset. So the index is like, how far into this memory do I read before I read that particular element? So the index can be thought of as, how many elements do I skip over in memory before I read memory for the element? The linked list doesn't quite have that, because you can't just skip over memory somewhere in the linked list. You have to follow the pointers to the locations. So when it comes down to it, an array, so the linked list looks like this. It's just all over the place. But the arrays are like really orderly. So in the same memory, this could be my array. And it's guaranteed in my array for these things to always be next to each other. Whereas the linked list has no such guarantee. So that's why my 2's down here in a random location. And if I made another one that was 3, for example, it could be over here. Or it could be up here, it could be anywhere. It's not guaranteed. So because it's not guaranteed, the only way we can do things is by following the next pointer. So I've got this loop here that says, if my pointer, my pointer to any of the nodes in the list is ever null, then I'm at the end of the list. But if it's not null, have a look at what's inside. So if I'm pointing to a node that exists, so what this will often do is print data will start off with a pointer to the head. So we can actually do it from this example here. My head will be pointing at the number 2. So here I will say the head was passed into this function and it wasn't null. Actually, I've got slides for this. I'm going to go back to my diagram, I think. So my n is a copy of head. So let me do the pointer n starts as a copy of head. This is in this particular piece of code here. N is not null because n's pointing at a node. So because it's pointing at a node, I'm just going to use the eraser so you can see where my cursor is. Because it's pointing at a node, it's not null, which means I can look inside. If I can look inside, I can pull out the data and print it out. And then I have this interesting thing here. This is the I++ of linked lists. N is now n next. So I'm going to take the value of n next and assign it to n. So n is this node here. This node's next is this pointer. So I'm going to replace n with this purple pointer. And pointers, we don't really care about the tail end of it, we care about where they're aiming at. So what I'm saying is if n is equal to n next, so it goes in here, looks at n, and then says, what's the next of this? This is pointing here. So I say that n is no longer aimed where it was aiming before, it's now aimed at wherever this thing was pointing. So it moves on to this node. And then the while loop executes, finishes, it comes back up here and says, is n null? N is not null because n's pointing at a node here, it's pointing at the node 1. So it will be able to look inside and print out the number 1. And then it will say n is equal to n next. If n is equal to n next, then 1 was pointing to null. Bit of a subtlety there, there's no such thing as pointing to null. Pointing to null means you're not pointing anywhere. So what happens then if n is equal to n next? So I will take a copy of the next, and it'll mean I am now pointing my n at null. Often we draw it like this, even though this point is really not going anywhere. Null, I've specifically not put null in a box because it doesn't exist. It doesn't have a piece of memory. Whereas, for example, the head is a piece of memory and n is a piece of memory because these things are storing memory addresses. Whereas the null is just an empty abstract concept that doesn't exist. So if n's pointing at null, I look at my code here and saying n is not equal to null. I'll only run if n is not equal to null, so I will stop there. The nice thing about that is I've gone through and I've processed every element in the list. I've identified it when the list is finished and I stop my loop there. So this is a loop that I think is very, very useful to know. and you will definitely be using this loop a lot. I mean, you won't have exactly the same stuff in it, but recognize this structure. You start off with a pointer to the start of the list. So this one's put into a function where we're expecting the start of the list to be the first pointer. And then anytime it's not null, you process it and then move on to the next node. And so once we get this, once we learn this process, we'll be able to loop through any linked list. Okay, and I've got another set of slides here, but I've kind of gone through and drawn this already. So we start with a pointer here, and when we're finished, we move on by copying this next. And eventually we hit the null. When we hit the null, we know that there's no more elements in the list and we've finished our loop. So, the example that we're going to be working on for longer than we've worked on any example in this course is the Battle Royale. So I got this idea from, obviously from stuff like Fortnite and PUBG, which is PlayerUnknown Battlegrounds. So these games that are super famous at the moment, because what they do is they have a whole lot of players at once, usually 100 players, and then all the players get knocked out until only one person remains. So out of 100 people, only one person wins at the end. And so we're going to use a linked list to be an assistant for a game like this, because a linked list works really well for example, removing one element at a time and still being able to maintain the list. So I thought this was a decent example for doing this. So what we're going to do is we're going to set up a linked list structure that tracks players in a game, and we're going to start by just building up a list of all the players in the game, and then being able to print out that list of all the players. We're probably only going to get to that point today, which is why I've only shown you that much so far. But as we work further with this example, we're going to think about maintaining the order of the list. So we could do something like try to keep this list in alphabetical order. So at the beginning, when we add all the players to the game, we're going to insert them in different locations in the linked list. So we're going to learn about insertion later. We also want to be able to knock people out. So to be able to knock people out, we need to be able to loop through the list and find someone, remove them from the list, and rejoin the list around them after they're gone. And that's really fiddly. That's going to be the third lecture, because that doesn't just involve moving pointers around and stuff. It also involves freeing memory at the right time, so you know that you free the memory of the thing that you've removed and stuff. Yeah, Zeal's saying free them. Yes. You've been knocked out of Fortnite. You're free, loser. Yeah. So we get that kind of thing. So we're going to escalate this complexity as we go along. So the beginning, we're just going to say, can we build up the list in the simple way? So that's the way I've shown you. And can we loop through it? And then can we build up the list in a more complex way? And then can we edit the list? Can we remove things from it? And then by the end of that, you'll be able to use linked lists for all kinds of really cool stuff. And strangely enough, your assignment, which has to do all of this kind of stuff to linked lists, will be due, 2 weeks after we finish working on all the lecture stuff on how to do it. So let's get started on this. We're going to need a node, right? We need a single node structure in order to build the more complex structure. So we're going to start with something simple, where the only thing we're going to track is the name of the player, and then the other node they're pointing at. Note that this is even in a different order than the previous struct we had, where we had the pointer at the beginning. Not relevant. Like, it doesn't matter what order these things are, but this pointer to another node of the same type must exist somewhere in this structure, or else it's not a linked list. And the police agree with me how important this is. I'm just going to let them go past. I just live reasonably close to a police station. I'm not necessarily in, like, crime central Sydney or anything like that. Okay, so let's go and start building this. Okay, what I'm going to do first is just move stuff to a different directory. Multi-file demo. I'm just making a directory there, and I'm going to move everything. Actually, I'm not sure that's going to work. It'll try to move itself. Let's see if it does. Everything into multi-file demo. Alright, couldn't move itself, but I think it moved everything else, which is fine. Okay, so just keeping my my organization a little bit clean here. I'm going to close this because I don't need those 3 files anymore. I'm going to close without saving because I've moved them. Very confusing. I moved them while I still had them open in the editor, which I probably shouldn't have done. Okay. So, battle royale.c. So I'm going to start a fresh file here. Battle Royale linked list demo. I won't put all the information in here right now because I just want to kind of get to coding, but I would definitely be normally putting information here about, okay, we want to build a list, we want to be able to print it out, we want to be able to remove people from the list one at a time and things like that. But for the moment, I'm just going to put this here, and I'll probably put the text in before I upload it later this afternoon. It's October, but we're going to switch that to November, I think, next week when we continue on this. This year's really burning up. Okay, so I wonder if I need any libraries. A couple of things that I know I'm going to do. I know that I am going to be allocating memory. So I'll have a standard library. I know also that I'm probably going to be printing stuff out. And even if it's not necessary for my program to print stuff out, often I will include the standard input-output library anyway, because I know that even if it's not printing stuff out, I might need to print stuff out to make sure this thing is working. So at least I'll have that. Okay, for completeness sake, I will have my int main void. I don't always put the return 0. A lot of time I forget it, and it's fine. Yeah, as Zeal, as you're saying there, for testing, I still might want to use my standard input-output. Having said that, I know that one of the things I'm going to do at the beginning here is going to be printing out a list. So I know I'm definitely going to use it. So at the moment, you know, it's the way I always like to start things. So you always remember this. It's like, I make it so that it compiles. Even if it does nothing, I make it so that it compiles before I start getting into work. So I know that at any point, if I just want to test this for syntax, I can compile it and there shouldn't be any errors. So if I didn't put this main in here, there would be an error. You're saying, like, you can't compile a program without a main. So at least that's all ready to go, and I can start with my node struct. I don't think I'm going to call this a node because it has a purpose. And remember, like, the kind of ideas that we're always going to follow when we're naming functions, variables, or a type like this is we name it for what it does. So these nodes are going to be tracking players in a game, so I'm going to call them a struct player. And the key element of this is a pointer to another struct player. So struct player pointer. When I'm building linked lists, I like to always use the word next to name these. So there's a player pointer next, and next is going to be the next player in the list. Keeping these always named the same every time that I use linked lists means that a lot of my thinking around things is easy. I can always read this word next and know that that's the link to the next element in the list. The other thing that we were going to do was store the player's name. So that's going to be a character array. If this is going to exist here inside this struct like this, it's going to need to have a specific size because we need to know exactly how much memory is going to be used for that struct. So I'm going to hash define a max name length. Let's keep it short because I don't expect in a game like this for people's tag to be so long that it like takes up too much of the screen or anything like that. I guess it depends if people have like excessively long like clan tags and names and things like that, but at that point we expect the system to have probably dealt with that beforehand and not have a name that long. So we get our max name length here. Okay, so there's my struct, and I know I can use that to build linked lists. So the next thing we're going to need is a function that is going to be able to create a single struct. So Trent's saying, yeah, don't do what Fall Guys did and let people use HTML and display names. So they then were able to cover the entire screen with a link to something. And David's, make your name 3,000 characters long so nobody can see you behind the wall of text that is your name. There's a funny webcomic that there's like this phone call that says someone saying, dear person, thank you for enrolling your child in our school. We had a problem with your child's name, which was closing brackets drop table, and now yes, David, it's an XKCD comic. And it's like closing bracket drop table, which is like something that will end a SQL database command to delete the table of information. So it's like basically when they enrolled that kid with the weird name in the school, what happened was instead of it being contained in a string, it had a closing bracket which would shut off the commands and then cause the entire database to wipe itself. And like at the end it's like, oh yeah, little Bobby tables, always doing great things. Yeah. So we're not going to do anything like that. Anyway, here in our create node, we're going to have a name. We might actually do that with a pointer. And the pointer to the next node, and we memory allocate. So this is actually quite simple because all we're doing is memory allocating a new node and then just blanket just putting in what we've been given here. So to have a function, it's going to return a pointer to a player, because if we memory allocate something, we always need to give back a pointer to the thing we've memory allocated, otherwise we've lost it immediately. And we've seen what happens when we lose the pointer to allocated memory. Once we lose the pointer to allocated memory, it's a leak, and it's gone. There's nothing we can do with it then. So the function is a player pointer function. So here's my type for the function, and then the name of the function is going to be create player. The information that's going to go in is whatever information is needed to fill out this struct. So we might have its name. I'm going to go with the pointer notation for this. If I wanted to, I could say specifically a character array, and it would work much the same way. When I put empty array, things like this, I always have this instinct that I want to put the length in. So I could say max name length in here, but that wouldn't necessarily work, because the string that I'm receiving is not going to be necessarily a 100 length string. And if I specify that it has to be a 100 length string, that might cause some problems. So what I often do to get around my instinct to put something in the square brackets is to say, this is just a pointer. So tell me where the name starts, and I will have to read it until I hit a null terminator, and I'll say, okay, that's the length of the string, and then I'll dump that in this array here. I can do this more easily with string copy, right? String copy is going to do that for me. So I'm going to do it as a pointer because I'm going to be clearer in my function definition by saying that I don't know how long this is going to be. I'm just going to use it. Also going to assume that it's not more than 100 letters, so it could be a problem if it is. Then I am going to take a pointer, which is a player pointer. I wanted to call it next. I want to call these name and next, but I'm going to get myself confused because they're the same name that's in there. So what I'm going to do is go this. So this will just help me when I'm actually making this function to know which one's the new one that I'm putting in and which one's the old, well, not old one, the created one that's in there. I'm going to copy that, create this function. I'm just going to shift myself up to the middle of the screen, make it easier for you to see what I'm doing. When I create a new function like this, I always want to comment to say what's going on, because these functions don't exist in the context that they use. The context that they use is here in the main, which means when you've got this code just floating on its own at the bottom, or in a C file on its own, you need to explain it. Otherwise, people reading are just going to not necessarily know what's happening. This one's not too bad because it has a good function name, and it's really, really clear what it does, but I still always put a comment on because we haven't explained necessarily what we're returning and what we're doing with the input, which is what I like to have in these comments. Create player allocates memory for a new player and populates it with new name and new next. Returns, I'm gonna get my spelling right soon. Returns a pointer to the newly created player. Okay. So if we've got this thing that we want to do, we want to create a new player and allocate memory for them. Okay, so in order to do that, I need a pointer. So I've got a pointer to a player, struct player pointer. You'll notice that I say pointer whenever I type in an asterisk, which will be good until I start doing maths, and then I will say pointer when I'm multiplying things. But here is the type of what I'm creating, struct player pointer. I will call it new player. And that new player is going to be allocated in memory, and how much memory we need, we're just going to ask how big a player struct is. So, as I said before, on Tuesday, you're going to see this line again. This is the bog standard memory allocation line that if you only learn to use this line for memory allocation, you will still be able to do nearly all memory allocation you ever have to do. So, we allocate a certain size of memory and we maintain a pointer to the same type. So this means that this pointer will work properly with this memory that's been allocated. Okay, so now that we have that, we can start using it, and we can say we're going to copy the new name into new player, which means I want to use string copy. In order to use string copy, I'm going to need the string library because I need to know what that function is. So I'll include the string library, and I'll say we're copying into the new player's name, and the string that we're copying in is the new name. We are also saying that the new player's next pointer will be this input next that we've been given. So, oops, I suppose press tab there to autocomplete. Okay, new player's next, making sure, yes, the pointer is next, is equal to new next. Note that there's no stars here. I'm replacing a pointer with another pointer, which means I don't want what's at the end of the pointer, I want the pointer itself, which is why I haven't used the star. Remember that if I use the star on either of these pointers, what that would do is would take me to what it's aiming at and look at that variable. I'm not worried about that variable. I'm actually saying, what did you want my next pointer to be? And I'll put that in place of whatever may have been there, which is actually nothing at the moment because we've just memory allocated. So this is us initializing both the name and the next pointer that are inside this struct. Okay, we're done there. We're done building the struct, so we can give it back. Again, we are not giving back the piece of memory. We're giving back the pointer to the piece of memory. So we give back just the pointer itself. No star here. If we gave a star here, we would not be giving back a player pointer. We'd be giving back the player the actual memory of the player, which we don't want to do. So we want to give back the pointer, which is why we don't use the star. We give back the whole pointer. Okay, so now we have our create player function. Question says, so if you use pointer name, we can avoid putting the max name length in the square brackets. In a sense, yes. So this pointer name says I will accept a string of any length. I could also just accept a pointer to a character, but the implication here is that we're using a string. So this says that we're not limiting the length of the string. If I said this, that would still work. I just prefer it the other way. So if I said this still 100% works. I'm saying I'm receiving a character array that I don't know the length of, which is fine. But if I said this, then I would say I will only accept a character array of length 100. I actually haven't tried this with other length arrays to see what happens. They might even still work, but I'm not sure. So because I never use it. It's so funny. There's always ways it's like, this is a fundamental thing we can do in C, and I'm not actually sure what it does because I never use it. It's a funny thing that you do when you get caught up in habits of doing things. You don't often test all of the capabilities of what can happen. So the reason I'm doing this is so that we get we're kind of making it really clear that we don't know how long this array is going to be. It's just going to be something. Shai is saying, I don't know, this sounds silly, but why do we opt to use a struct function rather than calling a normal function that adds a new player? It's a struct pointer function. So this is the type of the function. This is what the function gives back. The function has to give us back a pointer because we're allocating memory. If we're allocating memory and we don't have a pointer, then we won't know where that memory is and we'll immediately lose it, right? So when this function finishes, this pointer here, the new player pointer is going to disappear. The new player pointer is the only thing that knows where our new memory is. So if we ever lose the new memory that we create, then we've created a memory leak instead. That's memory we can never get back because we don't know where it is. So that's why we give back the pointer. So this same pointer here, new player, is the one that gets given back. Yes. People are getting there in chat. I think people are having that conversation, which is good. I mean, this stuff is fiddly, right? The little stars. Like, now we have types that are 3 words long. Well, not even 3 words, 2 words and a weird character long. So when it used to just be like, oh, here's an int, or here's a double, it was easy to see. But now we're getting to this more complex thing where it's like struct player pointer is the type, and it's the type of the function, and it's the type of the variable inside the function that eventually gets given back. Okay, so we've got this, and now we can create the list. So who was it at the beginning? Adam was studying. Was it Adam? I think was studying Avatar: The Last Airbender to be ahead for today, and so there's a tiny bit of Avatar, but I put chicken in here as well for fun. So we're going to build a list in a really simplistic way, the same way as we were doing before, and I've got the same kind of thing where there's me first, and then chicken gets created, and then the head gets assigned to chicken. So it's that kind of way that we're building up a list. We can do that here in our main. So I can say create a pointer called head. And if I want to, I could start by just going, so at this point, yeah, Adam's like, so worth it, just for those names that I was using. Chicken's like my Momo. Maybe? Is she my Appa or my Momo? Hard to say. I can't ride her. So she's probably more my Momo. Just steals food all the time, right? Okay. Oh, sorry, if people don't know, Avatar: The Last Airbender, there's 2 animals that they have with them. There's a little one and a big one. And so I was just saying between those 2, which one chicken is. At this point, I've created a linked list. I've created a linked list with 0 elements in it. So my pointer to the head is empty, which means there's no elements in my list. So that's perfectly viable for me to do that if I want to. So that's the way I can start. And then I can say, David saying chicken is clearly one of the dancing dragons. Okay, so, what was I going to say? I got distracted by dancing dragons. I've got a list now with no elements in it. So if I want to add one element to the list, I'm going to be the player that starts first. Oops, sorry. I'm going to say, if I'm the only one in the list, then I'm the head of the list. So the head of the list equals create player. The first thing in create player is the name. So I can be the first one. And then the next thing in the list has to be the thing that node is pointing at. And at the moment, there's no nodes because there's nothing there. So there's not much that I can point at. If I want to, I could actually be very neat about this and say I point at head. So if I want to become the new head of the list, I replace the previous head of the list and I point at what used to be the head of the list. It just so happens that that's null, and that's fine because there's nothing else to point at. But what I do is I say, if I'm going to be the new head of the list, I must point at everything else that had been in the list beforehand. Just so happens that's nothing for the moment. So the cool thing is this format here, we can keep repeating this. So if I want to add chicken, chicken then points at me because previously I was the head of the list, and then the head gets moved to point at chicken. So we've seen this already. This way we can use to make a linked list. We're going to see other ways of making linked lists, but this is the most simple one to begin with. It's simple because it only uses one function, but it's just annoying because it's slightly backwards as well because we're building our list in reverse order. I could have just copy pasted that. We're going to add some more players because I like my avatar characters. So let's put just Aang and Katara in. We don't need to make this an exhaust. I'm not going to put 100 names in here. At no point is this example ever going to have 100 names in it. I'm not going to hit that point. Although we've got like 80 students here, we could put every single one of your names in. But I think we're not gonna do that. For purposes of the example, this is enough to build a list. At this point, I consider my code to be highly risky. Oh, you're an avatar fan. Name every bit. I consider this to be a bit risky because I haven't compiled or tested this yet. The other issue is like I don't even have anything I can test with. So one of the first things that I want to do when I'm working with a data structure like this is to create a function that prints it out. What I might do, I'll just reset this for the moment, is at least compile this. Just to make sure my syntax is correct and I haven't forgotten anything important. Okay, syntax is correct. I'm not going to bother running it because it doesn't run. It's going to put this list together, but I won't see what's happening. So the next thing that I want to do is here, print out a list of players. So I want to be able to loop through the list until I get to null and print out the players. I'm going to do that in a function. I wonder if I even need a type for this function. I don't think this function's giving me back any information. It's only going to be used to print information to the screen. So I think it's going to be a void function. What did I name it? Print players. Print players is okay. Yeah. And the thing that this is going to take in is going to be the head of the list. Because if it has the head of the list, then it can loop through the list, printing things out. So the head of the list is a pointer to a player. So it's a struct player star, struct player pointer. And I am going to call that, player list. Typos are funny sometimes. Okay, I'm going to call that player list. So what I'm expecting when I say player list is I'm expecting if you're going to give me a pointer to, don't drag that. If you're going to give me a pointer to a player, I expect that to be the start of an entire list. So you can see how sometimes when I name my variables, I'm naming them with a specific idea of the the implications, the connotation I'm giving to someone if they're going to use my code. Takes the pointer to the head of a list of players, prints their names, one per line. Let's go one per line. Okay, in order to do this, I need to use my new loop. My new loop is the thing that's going to loop through a list. So what I might do is do this really explicitly so you can see what I'm doing. So the first thing I'm going to do is always take a pointer to one of the nodes in the list, and it's going to start off as the first node in the list. So shorthand that a lot of people use for this is cur, which is short for current. So it's the current thing that I'm looking at the list. So it's a pointer that aims at the thing that I'm looking at, and it's going to start off by being a copy of the pointer to the start of the list. If I wanted to, I could have just used this player list pointer and just moved this pointer, but sometimes I want to make these things really clear and show you exactly what we're doing. Okay, so we have a pointer to the start of the list, and then we're going to loop through the list, and we're going to loop through, and we can check a node if the pointer wasn't null. So if I run this at this point, so if I run print players here on the head of the list, it would simply go in here and set this up. This would become null, and we would check it and go, I'm not looping, which is good because there's nothing to loop on. If I do this at any other point, like in here, there's going to be something there. So our pointer is going to start off as not null, and we'll be able to do something with it. In which case, if we're doing something with a non-null pointer, we should be able to print stuff out. So I can, let's use some of our new stuff. I can use fputs on current's name, and I need to remember what all of the inputs for fputs are. And so what I'm trying to show you here is that we will always be fputs. We'll always be potentially looking these things up. So I've got the character, the string there, the character pointer string, and the stream. So the stream is going to be where this goes. Oh, that's for a file transfer. Oh, they don't show it, but I think I'm going to use the standard output, which is the thing that's going to write to the terminal. So standard out. So send the name to standard out. Oh, then I might also, actually, just because I want to use all of these things, I'll put a new line on the end of that. So I just wanted to at least show you some of these things that we can use, like library functions to do with input output. Okay, so looping through, we need to actually loop. So we need to iterate on our loop, is to say that our current pointer will move on to the next item in the list. So our current pointer moves to the next item in the list, which means now we will be continuously moving along through the list like this, and our current pointer will move along until it is null, at which point it is finished. So this function, I hope, is going to print out all the players in the list here. So we can try this by calling print players on the list, and I'm pretty sure that everything that I've done there is fine. We'll find out when we test it. Goldtime's asking, shouldn't the /n be blue? I think it depends on how your syntax highlighting is working. For me, this one, single characters, values, if I put numbers in as well, they're all pink. So it actually just depends on how your thing is set up. Alright, I'm going to save this, compile it again, and see what it shows me. Cool. So now we have printed out the names that are in the list in the order that they're currently in the list. And the reason why these things are in reverse order of the order we put them in is that everything we put in becomes the new head of the list. So it's kind of like every time we insert something, it becomes the first element and the others get shuffled along. So that's where Katara ends up going first, then Aang, then Chicken, and then myself. Because it's the reverse order of the way we put them in. Because just the way we're building the list at the moment is just pushing them in and pushing them along. Anson saying printf is sad as is an abandoned arrow replaced by putchar. Having said that, this would actually be easier with printf. So if I just show you what printf would do. So printf percent string /n, and the string is current name. There's actually less code. So I mean, we could do it either way. You know what I'm going to do is I'm going to leave all of this in here, so at least you can see the use of those functions. But printf would do the same thing. So it's not necessarily superseded. It hasn't been completely replaced. It has its own capabilities. And in this case, when we're doing a line and a character, it is potentially easy with printf to combine it. So if I compile this again and run it, I should get the same result. I always say should, I never say definitives, because like I could have broken something. Yeah. So we're getting the same result out of printf as we got out of these other functions. They just have different potential uses. Okay, we are 1 minute over, so I should finish up there for now. But at least this is our first look at how to set up the structures for a linked list, a first way of building it. I'm going to say first way because we're going to look at other ways of building it, and our ability to loop through a list. So if we just remove this part of it, everything else in here is the fundamental loop to loop through a linked list. Okay, so I will wrap up there. That's the official lecture over. I'll take a quick break, we'll come back, and we'll have some question time, and I'll talk about what we're doing. Okay. So I think Sarvesh has some questions there. We'll talk about your questions in a second in question time. All right. See you all soon. When I next speak to you, you will have an assignment. So over this weekend, we will release the second assignment. I will also make sure that we've got a live stream happening next week, a separate live stream outside of normal lecture time, where we talk specifically about the assignment and anything particular about the assignment that anyone might need to know. Alrighty. See you all next week, unless you're sticking around for questions, in which case I'll see you in a couple of minutes. Alrighty, I'm back. Any questions anyone has about code or anything that I've been doing today, feel free to put them in chat now. I saw that Sarvash had a question there, so I'll answer your question first while other people are asking whatever they want to ask. So, Sarvash is saying, so player just stores the next pointer and the data that will be stored. Yep. And the functions kind of use that fact to accept and print. Yeah. So, if we, I think we can draw this in a. Actually, when you think about it, this drawing is kind of already that. But let's do a new one, so that we're clear on what's going on here. Okay. So this is a player. I'm zooming in a little bit here. And so inside here we have the name. Oops. Oh. Okay, just pretend that I drew that correctly. And this has a piece of the memory that the struct has, and then another piece of the memory is the next pointer. And so this thing is then going to go pointing at another one of these. So if I have my current pointer, which is outside of that data structure, and my current pointer looks at this node, it can access these two things inside this node. So it can access the name that's in there and the pointer that's in there. So what it's going to do first is it's going to access the name, and it's going to say, oh, I can print this thing out, and then after I've done printed this thing out, I'm going to replace myself with this pointer. And so this pointer says point at this thing. So if I replace myself with that, I then am no longer pointing here. I'm now pointing here. And that's how the while loop is going to do things. So the functions are going to pick up one node at a time. And given that node and its next pointer, it's going to then get access to all the other nodes. And then what we do is, like, every time we look at a node, we look at its next pointer, and we keep going until the next pointer is null. And once the next pointer is null, then we know that there's no more elements in the list, and we've finished there. So hopefully that's giving you some more information. So Adam's asking you about the explain when we would use a type def. So let's go back to what did I call it? I knew a multi-file demo. Okay, so let's go into, just going to tab complete that, because I realize now that me using a hyphen and an underscore in a directory name is just going to confuse me every time I try to type that out. But lucky I can tab complete that. So let's go in here and we'll open all of these and have a look. Sarvesh is asking, let me finish your question before I move on to Adam's. Whenever we want to declare nodes for functions and stuff, we use struct. Yeah, so this is important, that when we create this, I can't do, let's say for example, player, let's say I want to make a new player. This is not code that works. So this code does not work. I can't say player, new player. The type that I've created is struct player, not player. So the keyword struct tells my compiler that this is the type. And so this works. So anytime we want to use a struct that we've created, this is the struct that we've defined here. Anytime we want to use it, it's a 2-word type now. So if I want a function that returns a pointer to a player, it has to return the pointer to struct player. We can't just use, for example, player on its own. So the struct keyword is now permanently attached to player, in a sense. Well, I mean, unless I did something else where, like, this is really, really bad, don't ever do this. This will like, cause you no end of confusion if you then reuse that word in another variable. But in general, once we've created a struct for something, these two are now linked together forever. So the type of this structure is struct player. And so anytime we're going to make it, it's struct player, and I can have pointers to that type as well, which I'm going to be using a lot. Giro-chan's got a fun question there. Why are C library functions neither in camel case nor snake case? I think they predate it. I think that a lot of the C library functions, when they were first written, they were written before we were even kind of using multiple words in the function names. I don't know for certain, but I think that we'll find that nearly everything in the C standard library is also 8 characters or less. We may find that case. So there's so few characters, like, because they're back in the time where like we only had 8 characters for a lot of things that we could do, and I think that you'll find that that's the case for everything in the C standard library. It's actually an older format, and we can't it's hard for us to future-proof it now because we need current C code to still be able to, current C compilers to still be able to use old C code. So there's this kind of issue like that, which is why they, like, because even string copy doesn't split its words in either of the ways that we would have split our words. Also, we would have spelt it out as well, because just that abbreviation is just like, I know it hurts my mind as well. But I think that, I actually don't know that for certain, but I'm pretty sure that the initial creation of the C standard library predates both camel case and snake case's existence. Okay, so Adam's question there. Let's open up these files. So the main, the person, and the person.h. So this goes into more detail than we need to talk about right now. I'm definitely going to talk about this in week 9, is how this person thing works. So when the main includes the person, it expects it's getting access to a data structure and a set of functions that can manage that data structure. So the data structure is here defined as a struct, but the main doesn't know what that data structure is. So instead of thinking of it as a specific type and data structure, it's going to think of it as this abstract type. It's actually the name of this term. They're called abstract data types, but we'll go into that later. So at the point at which we have data that we don't want to be accessible, so we want these functions to be accessible, but we don't want the data to be accessible because we want the functions to control access to that data. That's where we'd use a type def. So the type def says to the main file, if you're going to include this h, you're going to, like, it's nearly like a request. So we're going to use this, you're going to use this. Please use this so that you don't get into the idea that you have access to a struct. So that when you're using this from the main, you see this abstract idea of a person, and you don't think that there's any information inside it. So you can use it by saying, can we give it a power? Can we display something about it? Can we create them and things? But at no point in any of these is there idea that person is even a struct, that person has any internal workings or anything like that. So we just use it from these functions, and the type def makes this super clear, so that in my main, no pointers, no struct, only capital P person, and I know that I can't dig inside it. And that means that in here, in my C file where I've got this struct all set up, I know that no one can see it. So I know that the only thing they can see is this part of it, and at most they have an understanding that when they say capital P person, we're going to deal with that as if it's a pointer to a struct, which is going to be, because we're going to be memory allocating it, so it's always going to be a pointer to a struct. So it makes this kind of thing easy. So we say capital P person is something we've memory allocated, and then from there on, we can just use that. And on the outside here, capital P person can be created using create person, and so you can see how you could use your super technical person who is like deep in the low level C to write this part of the file, and then the person that's thinking about how the flow of the program should go to write this part of the file, and you can see that this person here is working nearly in English. It's much easier to work with this side because of what we've provided here. And depending on your place in an engineering team, you could work on either one of these things. We tend to just bounce back and forth most of the time. Yeah. So the type def is the thing that protects this specifically from direct access. I don't know if that helps. So hopefully, like me talking around it gives you a bit more information on what's going on there. Okay, Nace is asking, if you compiled person.c and main.c into a single program, why can't main.c access the variable in person.c? So this is interesting, because when we would compile these things, my main will be able to access anything that it has read previously. The only things that it explicitly has read previously is what is in its include. So if it includes person.h, it will see only these hash defines and then these function declarations. So the only things it can definitely look at is that, even though we're compiling these things together, and if I want to, I can compile person.c first. Oops. And then main.c. I can't remember what I called the person demo. Even if I did it like this and said, read this one first, then this one, the main.c, just because of the way it's set up, will still not look at anything that's in person.c. Because what person.c will become is it'll have been translated into something else. The only way that main.c will hook into anything there is if it knows what the right hooks are. And the only way it can know the right hooks is by having seen them in this file. So we'll only attach to the things that that it can see in the H file. So it's interesting because, yes, this stuff technically will have been created by my compiler. It would have been translated into code that can be used in the compiler, but it's nearly like an agreement. The agreement between the main, the H, and the C is the main says the only things that I will see that I can know are these function definitions, and when I say create person, I will then be given access to this, in a sense, to run, but I will not necessarily. It's nearly actually what main will do is main will say, hey, person.c, I know you have a thing that can do this, create person. If I give you my input, can you do it for me? And then it jumps into person.c, and person.c says, yes, I can do that for you because you're asking the right question through the H file. Person.c runs stuff, and then it gives back something that the main can then store. But it's nearly like the main will never actually see what's happening in the person.c. Even though it's on the one program, you've got this kind of delegation of control, I guess, where the main says, I control my stuff, and then when I give information to person.c, I give up control of that until it gives me back things. So they're kind of compartmentalized. They're all able to run and do stuff in the same program, but even within that program, we limit what main can do to only what it can see in person.h. So it's not that you can't, if you were to hack into it, in a sense, and get the memory location of this struct definition, and then you could definitely do stuff with it. So there's ways around that. Not going to go into detail on this, but there's a way to have pointers to functions. You know how we have pointers to variables, pointers to memory locations? There are actually functions that you can have pointers to, because functions also exist in memory, and you can run functions via pointers. I'm not going to say anything more about that, super complicated, but there is a way, in a sense, to dig into person.c read into the memory directly and find out this information and potentially use it in here. But we don't do it because it kind of breaks the agreement that we're not going to touch that stuff. Because when we have the agreement not to touch that stuff, then we're safer. So in the same way, we go back to that car analogy, you know, how I was saying, when we turn the wheel or we press the pedal, we expect something to happen to the engine. We've delegated that to the person.c. But there's nothing stopping me from walking around my car, popping the hood open, and then poking at things. I've just agreed not to do that because I don't know what I'm doing with it and I don't want to blow up a car in my face, you know, something like that. So while the main can technically get access to these things, we make it difficult for that to happen, and we kind of agree not to do that so that we don't make mistakes. And so part of that is actually this type def for us to say, let's just not even think about it as a struct. Let's think about it as a concept. This capital P concept. It's just something random in a sense, right? And if we think about it as that concept, we'll never get into the idea that we want to dig into it and start playing around with it. Because if we start doing that, we can cause problems. So it's this kind of like separation that's not a complete separation, but it's enough that we can think about it conceptually, so as we don't trip ourselves up as often. So I think if you think of it like that, it sort of starts to make sense that it's nearly not even that the program can't see it. It's nearly that the program has decided not to see it. Because everything that we compile, every function that we compile, is in here. And it's in here as a runnable set of instructions. Which means that if we knew how to access this stuff, then we could get access to all of this code. And usually it's through this. So we say this name that we can call in here links up with something in here. So long as they're all the same name, we can get that link that goes through and then gets that stuff happening. But the interesting thing is that we can't see this one. So here, all we get is we don't get a definition of a struct. We only get the type def saying that you can use this capital P. At most, you know there's a pointer to something that you don't know exists. So at this point, when the main looks at this, it just assumes that struct person exists somewhere, but we don't really use it. We're going to use capital P person instead. And we don't know what's inside, so we can't really pick at it. So I think I'm talking myself around in circles here, but hopefully that's giving you a bit more information about what's going on. And Nace is asking, yeah, this is a really good question actually. You're looking at all the details that's going on here. When we compile with our file, why don't we also need to compile the C files of the libraries themselves? I actually glossed over this a little bit. The difference between compiling a library with the angle brackets and compiling our own files with the, including the angle brackets versus the quotes here. The quotes means it's our file, the angle brackets means it's the C standard library. When we include something for the C standard library, we assume that our C compiler knows that if we want to use that, it can pick up the code that it needs. Some of these are actually header-only files. So they're files where the only thing that you need is the header. You don't need a separate C file at all. I'm not sure exactly because I don't pick at the compilers or at the C standard library that much to see what's going on, but as far as I know, you only need to include these and your compiler will find the rest of the code. Because in a sense, like when you think about it, these files, like if I just go, oops, had a compile command halfway running there. I hope I didn't do something weird. I go to my COMP1511 directory and I have a look. I can go to any of my directories and I can have a look in any of them. I will not find this file. Right? This file belongs to my compiler. So what I'm doing is I'm trusting that if I import the library that I get all of its functionality. So I actually don't know what the specifics are, whether there's a C file attached to this that my compiler knows about and it knows to use it, or whether it only needs the header file and everything it needs is in the .h file. I haven't looked at these carefully to see that, but I know that these are the two ways that it can be done in other C-like languages. Yeah. So, but I mean, I think that's an interesting question, because you're noticing that if we want to use the functionality in person.c, we need to compile both files, but in the library we don't. So the C standard library says, if you just include it, I'll deal with the rest, which is why we look at it differently between the angle brackets and the quotes. The quotes is our own file, and this is expecting this to be in the same directory that we're in. We can do other things though. So if it's in a directory above, I can go ... to say go up one directory, and then look there for this person.h. You'll see, if I don't know how much other C code that you look at, but this often happens, where the library files are kept in a separate directory called lib, which is, that shorthand again, short for library. And so we will look elsewhere for our library files like this person.h in order to find it. And so often, like when projects get bigger, we'll separate things into different directories as well, so we can organize what we're doing. So we don't have all the files for our multi-file project just all in the same directory. They'll be in different directories for their purposes, and we can find them like this. Whereas these ones are never actually a direct path to a directory that we're looking for. These are us saying to the compiler, can you just go and find this thing for me? This is something that you provide, not me. And this is something that I provide. Cool. Hopefully that gives you a little bit more information, Nesa, about what's going on there. Yeah, no worries. You're welcome. All right. I think I should wrap it up there. I think we've answered a lot of interesting questions that people have there, and I think the questions have dried up for the moment. So, I will wrap it up there. Thank you all very much. We're looking Sunday evening, I'm expecting, for release of the assignment. It depends. We've got to... I don't know if anyone has Tammy as their tutor, but Tammy's cramming to get that a few bits of that assignment finished, and I'll also be working on it on the weekend. So we'll try to release Sunday evening, but either way, whether it goes out on Sunday or Monday morning or something, the next time I see you on Tuesday, you will have the assignment in your hands and you can have a look at it. I will schedule a live stream for, I expect, Thursday next week, to give you a few days to read the spec, get some familiarity with it, and then I'll clarify things in the live stream. Okay, see you all next week.